We have considered the basic Black-Scholes equation, but this one can be extended in order to include different features in the problem. And here we're going to present possible different extensions of the Black-Scholes equation. Okay, the first one here is the options on dividend paying equities. So let's assume that the asset receives a constant dividend yield D. We are going to call it capital D. It's going to be the dividend yield associated to the asset, which is actually very, very common. That's in a time dt, its asset will receive an amount which is V times S times dt. And you have to include that in the Black-Scholes equation, and that's included in this way. You have this, the parameter D, that you have to include in the new Black-Scholes equation to solve whenever the asset receives a dividend yield. Okay, this is one. Another extension is currency options. So let's suppose that in holding the foreign currency, we receive an interest at the foreign rate of interest. So this F will be another parameter related to these currency options, which is the foreign rate of interest. And we have to include that parameter, which somehow is related. It's something similar to the dividend yield here, to solve in the new or in the extended Black-Scholes equation corresponding to currency options. Commodity options, another extension here. So in this case, the relevant feature of these commodities is that they have a cost of carry. So therefore, we need to introduce a Q is going to be a parameter, which is the fraction of the value of the commodity that goes to pay the cost of carry. So you have to pay something to carry them. So that's just like equivalent to have a negative dividend, and you have to include it here also in the extension of the Black-Scholes equation. You can see here it's like a negative dividend here. So let's go for another one. Another extension of the Black-Scholes equation are options on futures. The future price, we're going to denote it by F, capital F, of a non-dividend paying equity is related to the spot price the following way. This is the future price. And we can easily change the variables and express that in terms of this instead of S, in terms of F. And we'll have, therefore, an equation in terms of the new variable, which are the U, which is the expression for the function, which is writing just in order to, instead of writing in terms of S, we're writing in terms of F, which is the future price. And that would be, therefore, the extension of the Black-Scholes equation for future prices. Okay, let's suppose another extension is that the options on time-dependent parameters. If we do have that the volatility or the interest rate, they are not constant, but they are some function of time. And let's suppose we do know which are these, they are known functions of time, we have to include them here. If they have a time dependent here, we have to include that time dependent in the Black-Scholes equation. So that will be, in this case, the modified Black-Scholes equation that includes that time dependence of the parameters. But in this case, of course, then there's no way of solving that equation analytically. The only way of solving that is just numerically. Another extension is it's called power options. An option with a payoff that depends on the asset price at a maturity raised to some power. In this case, we'll call it alpha. That's P. It's going to be S2 alpha. So we can write now the Black-Scholes equation. Instead of writing in terms of S, we can write in terms of P, and the equations expressed now in terms of P will be given by this one. These are, therefore, the Black-Scholes equation for power options. And another extension is there's a possibility of having two-factor options. So we do have that in our basic Black-Scholes equation. The only stochastic term which is associated to S. But let's suppose that the interest rates are also stochastic, and they follow that being a process here. So in this case, which is not correlated to the asset, so in this case, we have to include the stochastic contribution of R here in the Black-Scholes equation. And it can be proved that the new Black-Scholes equation, it will write in this way, where in this case you have that the V will depend on S, will depend on R, will depend on time here. Therefore, here in the Black-Scholes equation, we have the second order derivative of V with respect to R, and the first order derivative of V with respect to R. So it will be like a three-dimensional equation because it will depend on three independent variables here. Another one, this extension of the Black-Scholes equation, is instead of having European options, we have the possibility of early exercise options. So these options can be exercised early prior to maturity, and they have different names depending when they could be exercised. So these are American, Bermudian, and many other different names. But the important thing here is that they all follow the same Black-Scholes equation. The only difference is that when do we need to apply the boundary conditions in order to consider the possibility of early exercise. And this is the most difficult thing associated to these equations here. And of course, you can build many other different derivatives. Actually, you can invent them. They are, and then propose the extended Black-Scholes equation associated to that possibility. So here we'll center our analysis or numerical analysis on the simplest Black-Scholes equation. But the interesting thing of that is that our main strategies could be applied to the different extensions to this basic Black-Scholes equation as well.